All right, the second example we're going to do here is actually significantly more straightforward than it appears. Let's say you have a person lying stationary on a hospital bed. Gravity is going to pull downwards on them, and they may experience a force of 700 newtons pulling down on them due to gravity. Based on this information, what you should be able to determine is the force exerted on them by their surroundings. In other words, by the bed underneath them. And from a medical perspective, it's this force that we're going to find which actually causes things like bed sores to show up. If you've ever been on like a drop tower or an amusement park ride, when you're falling, you can't actually feel gravity. However, you can sure feel when you hit something that stops you. Now, the trick to solving this problem, as with any other problem, is to determine the net force. Now, interestingly enough, you can determine the net force here very, very quickly. However, it is a little tricky because the thing that you need to find the net force in this particular problem is actually hidden here in words as opposed to numbers. Where you can find information that will help you find the net force is right here when you're told that the person is stationary. Now, if you're stationary, you're not going anywhere. If you're not going anywhere, your acceleration is zero. And if your acceleration is zero, your net force must reflect this. Right? Because your net force must be equal to your mass multiplied by the acceleration that you see. If you see nothing, the net force is zero. And it's zero in all directions. So you can leave it as just zero, or if you want to be consistent, you can write this in Cartesian notation as simply zero in every direction that you're going to look at. Right, so that's the trick sometimes to dealing with this. Sometimes your net force is in there in words. So pay very careful attention when you're reading problems for words such as stationary or at rest. They are telling you something. And keep in mind, the net force must reflect the acceleration, which is what you see. If you can see the motion of something, you can see its net force, so long as you know the mass. Now, with that being said, there are two forces here. There's one from gravity, and then there's this other one. Altogether, they got to add up to zero. In other words, the force of gravity plus this force from our surroundings has to equal to the net force, because all individual forces must add up to this total. And we know that this total is zero. So with this, we can actually find this force due to the surroundings. Again, we have to use vectors here, but the idea is it's another straightforward application of vector algebra. Now, for the force of gravity, we've been told that it's 700 newtons downwards. So we're going to put it just as 700 newtons in the y. And as for the force of the surroundings, that's what we're trying to find. And together, they have to add to zero all the way around in every component or in every direction. Now, with this being said, we can find this force due to the surroundings. The force due to the surroundings, in order for this to work out algebraically, has to be 0 in the x and 700 in the y. So in other words, it'll be 700 newtons up. Right, and that's basically it. What you'll notice is this idea that the net force is related to the mass times the acceleration, and all your forces must add up to the net force, solves pretty much every problem that you're going to deal with forces. We're going to be dealing with a couple more advanced techniques in dealing with Newton's third law and what that means, but this methodology is fairly robust. If you know how to deal with vectors, you can deal with any arbitrary force problem you've been provided with. The reason I go through this example is be careful when you read. A lot of times there are words hidden in the text that are actually important. So you need to be able to parse through it and find them.